All right, welcome to Unit 5 on sampling distributions. In this video, we're going to talk about topic 5.7, sampling distributions for sample means. I want to make sure everybody's crystal clear what we're going to be doing because this is very similar to what we've been doing in the past with proportions, but now we're working with means. In this topic, we will explore how to build a sampling distribution for a sample mean. This would be a model that represents all possible sample means of the same sample size taken from the same population. So the idea is this: if we take a sample of data out of a population, we can get a mean from that sample. But we could take another sample out and get another mean. We could take another sample out and get another mean. We could take another sample out and get another mean. As long as all of our sample sizes are the same and we were taking them from the same population, we could build a sampling distribution to show us what all of these different possible sample means could look like. But first, we need to talk about proportions versus means. Because moving forward in this class, if you haven't realized it yet already, there are two big things that we focus on: proportions and means. So before we move any further, we need to understand that working with quantitative data is very different than working with categorical data. The population proportion is one single value that does not vary. So when we're working with categorical variables, we're working with words, right? For example, the color of Skittles. Those are words: red, orange, yellow, green. Now, if we know that in the population of all Skittles, 20% of red, that is a single population value. We call it a population parameter. That would be the true proportion of red Skittles is 0.20. That value does not vary. That is the value for the population. It's not going to vary at all. Let me make this even more clear. Let's say that a casino that has tons and tons of poker chips, 60% of all the poker chips are blue. Okay, again, this is a population proportion that does not vary. Let's look at a picture of it. Here it is. Very basic picture. This is all the poker chips out there. 60% are blue, and the remaining 40% are not blue. So the true population proportion of 60% has no variation. It is 60%. That's it. There is no population standard deviation. Poker chips are either blue or not. So in terms of what's true for the population, there's only one number that's true: 60%. But when we start looking at samples, let's just say we take a sample of 80 poker chips, that number could vary. So if we were to take a sample, maybe we get 58% that are blue. Maybe we get 61% that are blue. Maybe we get 51% are blue. Maybe we get 70% are blue. Okay, sample proportions, yes, they are going to vary. So when we build a sampling distribution for proportions, that sampling distribution is showing us how all those samples will vary. Yes, we expect 60% right in the middle because that's what's true. But the sampling distribution shows us all those different sample proportions and that they are going to vary. And we have learned that we can calculate that standard deviation using a pretty basic formula, not too difficult. And we can understand how that varies. All right. Well, when you work with quantitative data, which is, again, quantitative data, think numbers, right? Data in the form of numbers. Well, this is a little bit different. That is because when you look at the population distribution of quantitative data, it will vary. Populations, populations do have a mean, a true mean, but every individual within that population is going to vary. And it might vary by a lot. So this is very different than proportions. Proportions is one set number. 60% of all poker chips are blue. Okay, well, if you're talking about the weights, quantitative variable, of giraffes, wait a minute. I can't say that all giraffes are 10 feet high. Whoa. Giraffes vary. And sometimes they vary a lot. Let's look at an example of students, right? Here is a distribution of the population of all the weights of students. Weights are quantitative, they're numbers. So here is all the students. Now, this data set does have a true mean, right? I mean, if this is a population, there is going to be a mu, one number that represents the mean of all the students. But each of those individual students are going to vary. And that's why there's a standard deviation that comes with that population as well. Again, with proportions, the population is one number. There is no standard deviation because populations don't vary for proportions. But for means, the population is going to vary. So if we were to take a sample of 30 people from the previous data and look at the mean of their weights, all right, maybe we get 120 pounds. Maybe another sample comes back 121.2 pounds. Maybe another sample comes back at 123 pounds. Maybe another sample comes back 150 pounds on average for that sample. So once again, samples are going to vary. We could then ask ourselves, well, what would a picture of all those possible sample means look like? Well, hopefully by this video, you're going to learn that's going to look normal. Right smack dab in the middle is going to be the mean that we expect, the true mean. And then again, this picture is showing that some sample means will be higher, some sample means will be lower. But what we have to understand when you're working with means is you got a lot of variation because now the population can vary. Any individual sample could vary, and even the sampling distribution that shows how all those samples are going to vary. So there's a lot of variation here. Now, what does this mean for us? What am I trying to get at? Well, honestly, it doesn't mean a whole lot. But what we need to understand is that when we work with means of quantitative data, there's always extra variation because not only does the population vary, but so will the sampling distribution. We did not have this problem with proportions. The population was one number. It is what it was. 60% of poker chips are blue. It doesn't change. That's the population. So samples are going to vary. We get that. When you're working with means, your population is going to vary. Your samples are going to vary. Your sampling distribution is going to vary. So there's a lot of extra variation that we have to consider. Honestly, guys, like I said, you don't have to worry too much. The formulas will take care of it, but you have to be knowledgeable of it. Now, let's make sure we get a picture of all this, right? So this is literally what I was just saying. So a population does have a true mean, which we call mu, and a standard deviation, because every individual, every giraffe will vary from that truth. So there's a standard deviation to talk about a single giraffe, how that single giraffe could vary. Now, if we just look at one sample, not many, just one sample, that one sample of, let's just say, 30 giraffes, that one sample is going to have its own mean, its own X bar. And within that one sample, there's going to be a standard deviation, S, for that one sample. But then what we're going to focus on this video is, of course, the sampling distribution. And this is where, sometimes symbols can get confusing. I'm going to do my best to explain them to you. But now we're talking about a mean of all means, right? Because we're not talking about one sample mean. We're talking about a sample, a sample, a sample, a mean after a mean after. We're talking about months, a lot of them, right? And now we're talking about the mean of all those means. So this new symbol pops up, right? And, oh gosh, all those means are going to vary. So there's a standard deviation for those means. Oh boy, so lots of symbols here, right? Proportions were a lot easier. But I hope by this video I convinced you this is still pretty easy, but you do have to understand how populations, samples, and sampling distributions all have a mean, and they all have some variation with them. Now, the last thing until we really dive into this is that I need you to also understand this. The mean of a bunch of samples will vary far less than any one individual. So think about this for a second. Out of all giraffes, and any one giraffe could vary a lot. I mean, just like people, right? So somewhere out there is the true mean of all giraffes, but there could be a little tiny giraffe that's really, really short, or there could be a really big giraffe. So the point I'm trying to make is that any one individual within a population could vary a ton. But when we take a sample out, and we take another sample out, and another sample out, those samples should not vary so much, because this no longer represents one giraffe, it represents 30 giraffes, and maybe there is a small giraffe within there, but there's a bunch of other giraffes that are not small. So the mean of a sample will be closer to the truth than any one individual. Same thing with this mean, right? First off, it's probably going to be different than this mean up here. But again, it's 30 different giraffes. But again, it's 30 giraffes, and I'm finding the mean of those 30 giraffes. So it's not going to vary so much as any one individual giraffe will vary. That's going to be a pretty important idea in this video as well. All right, so here we go. Let's dive into it. Keep in mind the big ideas that we've been talking about. One sample statistic. In this video, we're going to be focusing on a mean. So one sample mean, all by its own self, doesn't really tell us a whole lot about the population from which it was drawn from. If I just tell you, hey, I got a mean of 30 giraffes and it came back as a mean of 9.2 feet. Okay, great. Is that big? Is that small? Is that special? I have no idea. It doesn't become meaningful until we compare that one sample mean to all other sample statistics from all other samples of the same size from the same population, which is, of course, a sampling distribution. And we're hoping that that sampling distribution is normal. Hint, hint, it will be. So that way we could find some probabilities and move forward. All right, so here's the big question. If a sampling distribution contains a statistic for all possible samples, how are we going to build one? Well, it's really easy to do. All we need are three things. The first thing we need is the center. The center is literally the mean of all the possible sample means. I have to keep reminding you, and I'm going to do it until you get tired of it. A sampling distribution shows many sample means, all of the same given size. Now, the mean of all those means is going to be the truth. It's going to be the true mean. Now, I know you'd be like, wait a minute, you're telling me mu equals mu? That's stupid. That's easy. Come on. But no, you understand. These are different mu's. This is the mean of all of the giraffes in the entire world, where this is the mean of all my samples of 30 giraffes. But it would make sense that the mean of all my samples should have a center that is the true mean. But there is a condition that those samples have to be random to avoid being biased. All right. Now, obviously, if we are going to look at a sampling distribution which has mean after mean after mean after mean after mean, we know that all of those means are going to vary a little bit. Some are going to naturally be higher. Some are naturally going to be a little bit lower. It's just part of sampling. So the standard deviation of these means, the standard deviation of all these means, notice the symbol here, the standard deviation of all the means, it's very easy to calculate. You take sigma, that's the standard deviation of the population, and divide it by the square root of your sample size, the square root of n. So a lot of kids say, wait a minute, aren't these standard deviations, aren't these sigmas the same? No. This is the standard deviation of your population. This is the standard deviation of a bunch of means. So again, you have to understand that I'm using sigma because I'm talking about standard deviation, but that subscript tells me I'm talking about the standard deviation of a bunch of samples, whereas sigma by itself is the standard deviation for the population. But again, the condition here is that the samples have to be independent of each other, which means that if I take out 30 giraffes, I have to put them back before I look at another sample, put them back before I look at another sample, and that creates a little bit of a problem. And we've discussed this problem before. In the real world, we do not sample with replacement. When we take out, let's say, 80 giraffes, I was saying 30 earlier, doesn't matter. If I take out 80 giraffes and I replace them back, mix them up, replace them back. Again, that's just not feasible. Usually we sample without replacement. And again, we've heard this condition before. That is okay, as long as your sample size is under 10% of the population. So again, think about this, is that if you take 80 giraffes out, you have changed the giraffes that are left. You have taken out some of the population, and what is left is technically different. But that difference, we say, is negligible as long as our sample size is under 10% of the population. If you really need me to explain this again, let's think about batteries. How long does an average AAA battery last? Well, if I have a very small batch of 50 batteries and I take out 20 of them, well, there's only 30 left. I have made a significant change to the batteries that are left because I took out 20 and didn't put them back. But if I have a huge batch at the factory, if you take out 20, okay, technically you have changed what's left, but you haven't changed it a significant amount for us to worry about. All right, now the other thing that I want to mention for maybe the 18th time in the last little bit here is that bigger samples vary less. Bigger samples vary less. Sample size matters, okay? go back and look at our standard deviation formula. The standard deviation for a sampling distribution involves dividing by the square root of your sample size. So if I know that the average length of a battery is 450 minutes, that's the true average of all batteries, and the standard deviation for all batteries is 25 minutes. Now remember, that's a standard deviation for any one battery. Any one battery could be 25 minutes higher, maybe even 50 minutes higher, maybe even 75 minutes higher or lower. But if I look at a sample of 30 batteries, it's a sample of 30. It's no longer one, it's a sample of 30. So the standard deviation should be lower, much lower than 25. And that's why we divide the 25 by the square root of 30, and we get a very low standard deviation of 4.56 minutes. That's because I'm no longer looking at one battery, I'm looking at the average, the mean of 30 batteries. And here's the kicker. If I bump my sample size up to 250, my standard deviation for my sample means are going to be even lower. Now I'm not talking about one battery. I'm not talking about 30 batteries. I'm talking about the mean of 250. And the mean of a larger sample is going to be closer to the true mean. Yes, any one battery could definitely be 25, 50, 75 minutes higher or lower, but a sample of 250 batteries should not be that far away from the truth of 450. All right, the last piece is the shape of the sampling distribution. And of course, we would love for this shape to be normal, but all we have to do is check our condition. Now, we do need the sample size to be sufficiently large. With proportions, we have to look at successes and failures. With means, quantitative data, there is no such thing as success or failure. It's not like I'm a blue poker chip or I'm not. I'm happy or I'm not. No, right? These are numbers. So this is where we need the central limit theorem. The central limit theorem says, hey, listen, as long as your sample size is 30 or larger, you are sufficiently large to be normal. All right, let's talk a little bit more about the central limit theorem. I know we have talked about it in previous videos, but let's just talk about it a little bit more. If you really want to know the precise central limit theorem, here it is right here. The central limit theorem tells us that when you draw a sample of size n from any population with a mean mu and a standard deviation sigma, the sampling distribution for a sample mean is going to be normal, provided that the sample is 30 or larger. Now, this is really important, because this means that even if we have a population that's non-normal, let's say maybe it's skewed either way, then the sampling distribution that represents the many possible sample means taken from that population will still be normal as long as the sample size is 30 or more. So, this is where you really got to understand that even if you have a population that is skewed right, okay, maybe my batteries are skewed right. Most batteries are down here at 450 minutes. Very, very few batteries last a long time. When I start taking sample after sample out, sample after sample after sample out, yes, each individual sample is probably going to be skewed, just like its big brother that you took it from, right? But when we look at all of those sample means in one model, it will become normal. And that is the power of the central limit theorem. Now, in green at the bottom here, it's important to understand this. If the population is known to be normal to begin with, well, then it's obvious that the sampling distribution that represents the many samples taken from that normal population is going to also be normal. So in this case, a sample size smaller than 30 is actually okay. Central limit theorem really isn't needed. Central limit theorem is really only needed when your sample size is non-normal. That's where we say, oh crap, our population is non-normal. What do I do? What do I do? Well, that's where the central limit theorem says, hey, don't worry. The sampling distribution will still be normal as long as your sample size is 30 or larger. But if our population is already normal, to be honest, any sample size will produce a normal sampling distribution. So a lot of kids say, oh, I got to have a sample size bigger than 30. Well, actually, you don't. If your population is known to be normal, honestly, a sample size of 10 is going to be fine. All right, so in summary here, we need three things to build a sampling distribution. Don't forget what a sampling distribution shows. It shows us all possible sample means, all of them, taken from a population with mean mu and standard deviation sigma. So if we think about all those possible sample means, the center of them all, the mean of them all, will be equal to the true mean, as long as our samples are random to avoid bias. Now, those samples are going to deviate. They're not all going to be the same. So the standard deviation for our sampling distribution is taking the standard deviation of the population and dividing it by the square root of n. And that is, of course, as long as our sample size is under 10% of the population to assume independence. And lastly, the shape is going to be normal, as long as central limit theorem tells us that our sample size is 30 or larger, or, as I just mentioned, even if your population is known to be normal, then honestly, you could be any sample size. So don't get, too fixed on, I gotta be 30 or larger. That is true if you don't know anything about your population, but if you know the population is normal, then under 30 is okay as well. So, that's it, guys. This is pretty easy. Now, keep in mind, though, we do need to know three things to create a sampling distribution. We need to know the true mean for the population. We need to know the true standard deviation for the population. Again, we need to know the true mean because that's the center. We need to know the standard deviation because that's involved in the formula, but we also need to know the sample size. So with those three things, we could literally do it all. It's really quite easy. It's crazy that we don't even have to take a look at a single sample to understand what they will all look like as long as we know these three things. But I do want to emphasize kind of what I started with. With proportions, you only need to know two things, the true proportion and your sample size. That's because with proportions, populations don't have a standard deviation, but when you're working with means, populations do vary, where with proportions, populations don't vary. It is what it is. Samples always vary in either case. All right, guys. Stay tuned for the next video because there will be one following this one that will help you work through an example so that you can understand how to build a sampling distribution and find probabilities.